It was interesting, I think. No one would say it was boring. What I'd like, if possible, is those who take the test, if you're feeling altruistic, someone could type up the test as it happened and submit it to me, and then I'll upload it on the net so that everybody can see what these kinds of tests are like. I think that everybody who was in the test today will agree that the policy of this course is certainly not regurgitation. There's no parent work. It's all very much to do with being able to think on your feet and being able to use the results that you had from the notes in order to come up with new conclusions. But that being said, I was impressed with the performance of everyone today. And nobody today failed. Right? So everybody passed. I decide pass and fail before I do the written work. The written work then decides to mark. So everybody today who wrote the oral test passed the oral test. Okay. Today is the turning point. Everything we've done up until now would be called preliminary work. In other words, the coordinate transformations and all of these things that we did were preliminary. Today we begin our study in earnest of mechanics and of the subtleties of mechanics that lead us to that deep generalization of the ground. We begin our journey. And hopefully, if things go well, we'll get quite far along our journey. By Monday, I'm hoping to have proven the Grange theorem. And from there, the course will turn into a tutorial. There will be a large amount of problem solving, a large amount of interactive work, and just a few extra concepts coming up. But the speed at which concepts arise will be much slower than it has been so far. The structure of today's lecture, I will lecture as long as I need to finish the material I've planned. If I finish early, we will have a tutorial. How the tutorial will work is, as I go through the lecture, I'll raise questions. These questions will remain questions until the tutorial. During the tutorial, I sit back in one of those seats, and you guys take them on and answer the questions that we have raised. Right. Without further ado, let's begin. First things first, there are a couple of loose ends. From the work we've done so far. Now we considered, I'm not going to write a proper review, we considered coordinate systems, curvilinear coordinate systems, we considered rectilinear and so on and so forth. The point is, the last thing we did was transformation. We looked at scalars and we looked at vectors. So, my fellow physicists, what is a vector? Can I hear it?
Quantity that changes under a transformation, so it doesn't stay the same like a scalar.
So it transforms like a vector, right? And a scalar changes, scalar field changes like a scalar. Generally, we had a result that if we had a scalar function, f of x1 to xn, right? We could write that in another coordinate system, say q1, qn, or whatever, as f of transformation equations, x1 of q1, qn, xn of q1, qn. Right, so the transformation of the scalar was very simple. We transform a scalar field in a very simple way. We simply write out our transformation equations, and that's going to be our f bar of q1. Vectors transform in two places as opposed to one place. So a scalar transformed only on the arguments that we take in. A vector transforms both in the arguments that we take in and in the output parameters. So a vector field f I of x1 to xn, right? This transforms according to our either covariant or contravariant rules, depending whether we're taking a covariant or contravariant component. So we found out that it turned into E J dot the full vector of x1 of q1 to qn to xn of q1 to qn. Right, so we transform both what we put in and what we get out. Whereas here, we only transform what we put in. Right, that's really essentially the gist of transformations, and I'm not going to harp on it. Exactly how these functions look when we dockerized these things, we'll become familiar with them when we start doing real transformations. To see all this in abstract is really just going to be a bit too confusing and too distracting at this stage. So, I'm now going to look at a few things that emerge from these loose ends. The reason why I'm doing this is because it's going to lead me quite naturally into the kinds of considerations that are going to take us, transport us from mere Newtonian physicists into people who are able to apply elegant mathematics, solve real physics problems. So the first thing I'm going to consider is what happens when we transform Newton's laws. In particular, the second law. Right. Now, the reason why we look at this, and we did look at this already, very briefly, yesterday. I ran into the class and moved along the board like a Tasmanian devil. But we looked at transforming Newton's laws into polar coordinates. And we'll just very briefly do this again now, in some detail, just to understand exactly what's happening here. So what are Newton's laws? Newton's law, we all know, is F equals ma. But now A is a vector. So if I write these laws out properly, that's the x component of the force is the mass times d squared x by dt squared. I'm going to write this d squared x by dt squared, the wrong thing, as mx differentiated twice with respect to time. Have we all seen this dot notation for derivatives? Right, so who's a bit confused about the dots? Great. So I can then write the y component as y as my dot, and I can write fz, the z component as mz dot. These are the three vector equations of Newton's second law of motion in Cartesian coordinates. Now, it is one of the unfortunate facts of life, along with so many others, that Newton's laws are not transformation invariant. What that means is, if I change coordinates to polar coordinates, to spherical coordinates, to cylindrical coordinates, the form of these equations changes. We'll see that in some relief, in some detail now. The reason why I'm stressing it is because later when we come across Lagrange's equations, they don't. In other words, when we have Lagrange's equations, polar coordinates, Cartesian coordinates, spherical coordinates, the coordinate that gives the distance that a roller coaster has moved along a track will all be the same thing. We will write down the exact same equation, and it will miraculously work. So, I want to stress the shortcomings of this equation in this form. To do that, we're going to derive the polar form of that equation. So, how are we going to convert this to polar? Well, we should have something like a generalized force in the r direction is equal to something, and a generalized force in the theta direction is equal to something. When I say generalized force, I mean components of force in the sense that I'm multiplying it by a tangent vector like that. Right. So it's not necessarily even a force, and that's why I use Q. S implies that I'm actually talking about a force. These things don't end up always being forces because the tangent vectors themselves can sometimes have a dimension which messes things up. Right, a dimension that is not just that of length. So let's look at what we would expect if these things are transformation invariant. We'd say, oh, the R component should be mr double dot, and the theta component should be m theta double dot. And then we'd be really happy and smiling. But unfortunately, that doesn't happen. We can't just write it up. The reality is a lot more somber. In reality, we did a transformation yesterday. One way of doing it would be to follow those rules. And in the notes that I will hand you, chapter 2 notes, I will follow those rules and show how you can follow those rules to derive the polar coordinate version of Newton's laws properly according to vector transformations, things that transform like a vector. But we're mathematicians. If a shortcut presents itself, we take it. And a shortcut is going to present itself. Instead of going through the long process of writing out all these things in transformation equations and so on and so forth, we simply notice that the acceleration vector can be written very nicely in polar coordinates. Let's have a look. The acceleration vector is d squared by dt squared of this vector, x, y, position vector. What's the position vector? In polar coordinates, r cos theta, r sine theta. That's my transformation equation. But now I'm going to use my knowledge of the polar coordinate unit vectors, which are, what is the r hat unit vector? Cos theta, sine theta. And I can see it here. Right? There it is, cos theta, sine theta. It's multiplied by r. There it is, cos theta, sine theta. D squared by dt squared of r times r hat. Right. So having noticed this nice little result, I'm inspired, instead of going along that route, to go along this route and simply work this thing out. To do that, I need to know the time derivative of the unit vector, r hat. And as it will transpire, I will also need to know the time derivative of the other unit vector, theta hat. So I work those out. Over here. The r hat by dt is d by dt of cos theta sine theta is minus sine theta cos theta times theta dot by the chain rule. I'm differentiating with respect to time, not with respect to theta. So I first differentiate with respect to theta, and then differentiate theta with respect to time. Anybody lost on that step? Nobody lost it, okay?
So does it mean theta is also a function of time?
Theta is a function of time, right? So theta, like x or y here, is a coordinate, and therefore a function of time. It's something I must be able to differentiate correctly. So we have differential with respect to t, I use the chain rule. And anybody recognize this guy? Theta hat. I heard it on that side of the room. This is theta dot there, times by theta hat unit vector. Great. What about the theta hat by dt? Well, that's d by dt of minus sine theta cos theta. Now we're quite comfortable with using the chain rule because we already used it above. So we'll times everything by theta dot. So it's equal to theta dot times by, differentiate with respect to theta, what do we get? Minus cos theta minus sine theta. Well, that's kind of familiar. It looks like minus theta dot r hat. Yeah. The order is not important. Because we're multiplying by something that's a scalar, so it can go on either side. Right, so we now have the derivative of the unit vectors. And we can use that to compute this. Well, the velocity vector in polar coordinates is going to be d by dt of my position vector r hat. Correct? That is product rule. When I use the product rule, I differentiate the first component, multiply by the second, and then I differentiate the second component, multiply by the first. So that gives me r dot r hat, differentiating the first component, plus r times derivative of r hat with respect to time. And that's theta dot theta hat. Theta dot theta hat. So now I've differentiated it once, the position vector, to get the velocity. Differentiating again, acceleration is going to be the derivative of the velocity. d by dt of r dot r hat plus r theta dot theta hat. And that gives me, well, product rule again, r double dot r hat, when I differentiate the first component. R double dot r hat plus differentiate the second component. R dot times the derivative of r hat, which is theta dot theta hat. R dot theta hat plus, now I go to this term, differentiate the first component. R dot theta hat. R dot theta hat plus, differentiate the second component. R theta double dot theta hat. R theta double dot theta hat. Finally differentiate the last component, that's the theta hat, so I have r theta dot times derivative of theta hat minus theta dot r hat. I can simplify all of that. And I get an answer. The radial tangential component of the acceleration. So the acceleration is therefore equal to, let me group those terms in the r hat direction and those terms in the theta hat direction. So it's r double dot in the r hat direction minus r theta dot squared in the r hat direction. Plus, what about the terms in the theta hat direction? The theta hat direction is two of these guys, 2 r dot theta dot, and one of these guys, r theta double dot. So there's an r theta double dot plus 2 r dot. Right. So that is what the acceleration vector generally looks like in polar coordinates. If I've got some object moving through space, some particle, and I want to describe this acceleration, that's what it looks like in terms of the radial and tangential components at any point, regardless of the motion.
The R and theta unit vectors, you say. Looks like the I, J, K.
The r hat and the theta hat are your unit vectors, kind of like the I, J, and K. Only difference is, at a point in space, the r hat and the theta hat directions, there's your theta hat, and there's your r hat. So I'm saying I can express now my acceleration of some particle that's moving through space as a combination of an r hat component and a theta hat component, as opposed to a combination of an I component and a j component. Yes. Okay. So that's the acceleration vector. And I can now write Newton's laws out. F is ma, remember. So I can write is m times this, right? Now here's the important part. When I want to get the components of the force, remember the force is a vector, and it transforms like a vector. So I need to get its components, its r and its theta components, as opposed to its x and its y components. Right. And I can do that in two ways. The formal way that we described above, or we described before, was to multiply multiply by the tangent vector, to dot product with the tangent vector. That is how you get the generalized components of force. Right? Force is this object that changes when we change coordinate system, and these natural quantities that are expressing the change are called generalized components of force, and they are what we get when we say ER dot F and E theta dot F. And I write this one as QR, and I write this one as Q theta. These are generalized components of force. The important thing I want to stress is that they are not forces, both of them. This one's a force, this one's a torque. And this will come up again and again in the course. We'll understand it in more detail. I'm just kind of mentioning it at this point so that you're aware of it. This is different from taking this vector and expanding it in two different Cartesian coordinate directions given by the r hat and the theta hat direction. That would be giving me two real components of force in r hat and theta hat directions. So this is not in general equal to theta hat dot f, which I call f theta, right? So this is a real component of force, and this is a generalized component of force. Right. So in general, this is where we take a unit vector and find the amount of force in that direction, and this is where we take a tangent vector and find how the force looks when we take a dot product of the tangent vector. When we write this out as a sum, it looks like a transformation equation, and that's why this is a component. Whereas this one here looks like a component, a real physical component, and so it's a real component of force in each direction. Okay, I just need to make that point clear. But once it is made clear, we can look what Newton's laws look like in polar coordinates. QR is equal to, well, if I dot product, what's ER equal to? It's equal to R hat. ER is the unit vector. So, if I dot product it here, I get a 1, and here I get a 0. So QR is equal to M, remember there's an M in this whole equation, F equals MA, R double dot. That's looking okay, that's looking like what I expected by the smiley face. But hang on a second, what's going on? There's another term. Minus M R theta dot squared. Okay, that doesn't look like Newton's equations anymore. That doesn't look like F equals MA. F equals MA plus what? Right? And let's do the next one. Q theta is equal to, now E theta is equal to what? E theta is R theta hat. There's an R coming in there, right? So R theta hat when dot product in here gives me naught. Because theta hat and R hat is naught, that will drop in naught. And R theta hat when dot product in here gives me R. Right? So here I get M R squared theta double dot. Well, already that looks weird. What the heck is this? This isn't an M theta double dot. And let's try the next one. Plus 2 M R dot theta dot. That's just getting silly. We're completely out of the page. Yeah. So when I dot product, so E theta is R times theta hat. You okay with that? When I dot product E theta with F is equal to M times A, right? So I can put an M in front of these vectors, right? Now when I dot product theta hat with R hat, I get 0 because they are orthogonal vectors. When I dot product theta hat with theta hat, I get 1 because they are orthonormal vectors. But E theta is R theta hat. So when I dot product E theta with theta hat, I get R. Nice. So I get an R times in here. And that's where this comes. Does that answer your question? So sure. E theta R theta hat. So E theta dot F is equal to R theta hat dot F. Nice. And the theta hat dot then the rest. Right. Point is, this doesn't look like Newton's equation. This does not look like Newton's equations. It looks very funky. There are ways of interpreting this equation though, within the Newtonian framework. What we say is, this part looks okay, and this thing here is some kind of center-hugging thing that pulls me towards the center based on how fast I'm moving around the center. If I'm moving fast around the center, I need some force that's pulling me towards the center to keep me moving. That's essentially what it's saying. So if I start running around in a circle, the faster I run, the harder it is to stay in a circle. Because I want to shoot out tangentially. And I keep on applying a force to steer myself, a force inwards, a force towards the center, a centripetal force. So we call this guy as for this, Q theta isn't even a force. Q theta is a torque. Right? You can check its dimensions. It doesn't have the dimensions of force. Theta is dimensionless, so Q theta is torque. This is talking about the torque of some angular coordinate. Associated with an angular coordinate. And all of these guys have dimensions of torque as well. And you should check this for your help and for mine. Right. So these all have dimensions of torque, and these are different applied torques. And you'll see terms like this popping up a lot when you consider Newton's equations in different coordinates. And what we technically tend to call this is the applied torque, kind of like the MA part. And this guy is what we call Coriolis. A Coriolis force. So it's something that really results from when you're in a turning coordinate system. So I don't want to get too far into this. But there are terms in this equation that do not look like Newton's equation. Now, it's difficult in general to reason about arbitrary systems using equations like this. And here are things to do in the tutorial. We converted Newton's law to polar coordinates. Try converting Newton's law to cylindrical. And try converting Newton's law to spherical. I won't be evil enough at this stage to ask you to convert it to elliptic and cylindrical and ellipsoid, simply because those aren't orthogonal systems, and so we can't do cool fancy things like get rid of half of this vector by dot producting, because the dot product doesn't actually help us. So let's stick with orthogonal coordinate systems for now. Maybe in your assignments you might need to use other coordinate systems, depending on what you're chosen to do. Right, so the point is we used this, and we used it to look at the simple pendulum. And I'm going to just briefly review that with a very good motivation. My motivation is to ask what's special about using Newton's laws in polar coordinates for the simple pendulum as opposed to using them in Cartesian. Because we've all solved the simple pendulum before using Cartesian coordinates. It's not difficult. It's possible. You certainly do it. But in fact, there's some advantage gained. We'll see there.